Good morning to all. Chemical engineering thermodynamics, in which we discuss about the various property relationship between the uh, energy properties and as well as free energy. So previously we discussed about the uh, Maxwell's equations, relationship between each other's terms. Okay, so जैसे कि फ्री एनर्जी है, एंथैल्पी है, एंट्रोपी है. ओके, सो हेल्महोल्ट्ज इक्वेशन है, फ्री एनर्जी है उसका. तो ये सब हमने प्रीवियसली हमने डिस्कस किया था. नाउ द मोस्ट इम्पोर्टेंट थिंग इज दैट द नेक्स्ट इक्वेशन इज क्लेपेरॉन इक्वेशन. क्लेपेरॉन इक्वेशन, where it is used, why it is used, and how it's related with the Maxwell's equations. Okay, so first of all, let's start Clapeyron equation. It predicts the dependence of equilibrium pressure on temperature when two phases of given substance coexist. Where it is used, Clapeyron equation predicts, कहाँ पे predict होता है, the dependence of equilibrium pressure on temperature when a two phase of given substance is coexist. જ્યારે પણ જે બે ફેઝ છે એ શું થતા હોય, કોએક્ઝિસ્ટ થતા હોય, ક્યારે given temperature અને equilibrium pressure પર, બરાબર, ત્યારે. And it may be uh, given by this equation. So equation is that dp upon dt is equal to delta h upon t into delta v. रिलेशन क्या है देखिए, प्रेशर का टेम्परेचर के साथ रेशियो इज इक्वल टू द एंथैल्पी अपॉन टी इनटू डेल्टा वी. where delta h and delta v are enthalpy and volume change, बराबर. The delta, that means a change. Okay, so both are, this is a delta which is a change. Now this accompanying a phase change, this one is for a phase change because the data will be a change. Now it can be derived from Maxwell's relation equation number 6.23. ओके, जो मैक्सवेल का इक्वेशन है 6.23, वहां से हमने डिराइव किया है. सो लेट अस सी वंस अगेन. मैक्सवेल का इक्वेशन नंबर 6.23. ओके, सो वो कहाँ से डिराइव किया है, लाइक दैट, यहाँ से 6.23, जो क्या है, डेल पी का डेल टी के साथ क्या है, डेरिवेटिव है, और उसके साथ क्या है, डेल एस बाय डेल वी. तो यहाँ पे डेल्टा वी और क्या कर दिया है, टेम्परेचर इनटू डेल्टा वी. ठीक है. सो नाउ this equation is derived from the 6.23, which is applicable to any closed homogeneous or heterogeneous system in equilibrium. Okay, એ કોઈ પણ જે homogeneous, heterogeneous અને equilibrium વાળી સિસ્ટમ ને applicable છે with an external pressure. Consider a system containing a two phase, say liquid and vapor. આપણે શું કરવાના છે, બે ફેઝ ને લેવાના છે, જે શું છે, લિક્વિડ અને વેપર. બરાબર, આપણે ધારી લઈએ કે બંને શું છે, લિક્વિડ અને વેપર. ઇન અ thermodynamic equilibrium, by the phase rule, the system is univariant. Okay, system is univariate. In other words, only one intensive parameter can be varied independently. એટલે કે બંનેમાંથી ખાલી એક જ ઇન્ટેન્સિવ પેરામીટર છે, બરાબર, ટેમ્પરેચર અને પ્રેશર. તો એમાં બેમાંથી એક જ શું થશે, વેરિયન્ટ ઇન્ડિપેન્ડન્ટલી થશે. Then the equilibrium pressure, that means for the present case the vapor pressure, બરાબર, equilibrium pressure એટલે it is depend on the temperature only. What exactly depend, temperature के ऊपर depend रहेगा. And it is dependent of volume, and it depend on temperature only, and it depend independent of volume. volume क्या क्या रहेगा, independent. So the partial derivatives are del p by del t at v in equation 6.23 can be replaced by dp by dt without the constant volume restrictions. Okay, constant volume restriction. So moreover, del s by del t, del s by del v at t is equal to delta s by delta v, where delta s is the entropy change when a given quantity of the substance it is transferred from the one phase to the at one phase to other at a constant temperature delta v. Now, which is accompanying volume change delta s upon delta v is a given temperature. So both delta s and delta v are extensive quantity. It is not a intensive property, it is a extensive property. And the rate proportional to the amount of material transferred, as we are dealing with equilibrium and therefore with a reversible process, is delta s is equal to q by t is equal to delta h upon t, where delta H is the change in enthalpy during the phase change or latent heat of the phase change. Whatever. So substituting this equation into 6.23. So ये वैल्यू हमें क्या पुट करनी है, 6.23 के अंदर पुट करनी है, तो हमें क्या मिलेगा इक्वेशन, क्लैपेरियन इक्वेशन, which is given by this equation. Okay, so these are the Clapeyron equation. Now let us see various use of Clapeyron equation. Clapeyron equation may be used for various purpose. For example, it may be used to calculate the heat of vaporization. First जो important thing है वो कहाँ पे है? It is used to calculate the heat of vaporization. If the vaporization of vapor pressure with temperature is known, જ્યારે આપણને વેપર પ્રેશર ખબર હોય ત્યારે આપણે હીટ ઓફ વેપરાઇઝેશન આપણે કેલ્ક્યુલેટ કરી શકીએ. અલ્ટરનેટિવમાં જોઈએ તો હીટ ઓફ વેપરાઇઝેશન અગર આપણને ખબર હોય તો ઇટ ઇઝ પોસિબલ ટુ પ્રેડિક્ટ ધ વેપર પ્રેશર વેરિએશન વિથ ટેમ્પરેચર. તો આપણે શું કરી છે, પ્રેડિક્ટ કરી શકીએ છીએ, પ્રેડિક્ટ ધ વેપર પ્રેશર વેરિએશન. ઓકે, alternative derivation for Clapeyron equation is provided in chapter 8, example 8.3. Okay, now so next is that Celsius Clapeyron equation. So the relation is important. Celsius Clapeyron equation, if the temperature is not too near the critical point, if temperature is not too near the critical point, the volume of liquid in a small comparison with the volume of vapor, volume of liquid and a volume of liquid with comparison with the volume of vapor. So the change accompanying vaporization delta v શું થશે, gas અને liquid માટે if we consider a change, so delta v considering is that vg minus vl, therefore approximately equal to vg, the molar volume of vapor is given by the equation 6.25. It now becomes dp upon dt is equal to delta h upon t into vg. ઓકે, કારણ કે એ શાના પર ડિપેન્ડ કરશે, એપ્રોક્સિમેટલી હવે ઇક્વલ ટુ vg જેટલું થશે, બરાબર, વેપર પ્રેશર, મોલાર વેપર વોલ્યુમ ઓફ મોલાર પ્રેશર. નેક્સ્ટ, the vapor pressure in region will be, the critical point is relatively small, so that the vapor can be assumed to behave as an ideal gas. Okay, so the molar volume is Vg can be replaced by RT upon PV is equal to RT. ठीक है, तो PV is equal to and RT છે તો એના પરથી Vg ની જગ્યા પર શું લખી શકીએ, RT upon P. ઓકે, જે આપણને ખબર છે RT upon P વાળું ઇક્વેશન. So equation 6.6 it becomes બરાબર. So dp raised to p is equal to dt or ps into delta h upon rt square, because અહીંયા vg ની જગ્યા પર શું લખીએ છીએ આપણે, vg ની જગ્યા પર આપણે લખીએ છીએ rt upon p. ઓકે, so અહીંયા થઈ જશે rt square, અથવા તો it can be written as a in the form of logarithmic. So Clapeyron Celsius equation in the form of logarithm, it is d ln p s divided by dt equal to delta h by rt square. So this result is known as a Celsius Clapeyron equation. Okay, so equation number 6.27, it is known as a Celsius Clapeyron equation, and the equation are here. Okay, and equation, okay, now assuming that heat of vaporization is remain constant in temperature range from T1 to T2. T1 અને T2 ની રેન્જમાં આપણે જોઈ લઈએ કે ટેમ્પરેચર જે છે એ શું થાય છે કે ચેન્જ થતું નથી, બરાબર, કોન્સ્ટન્ટ રહે છે. સો 6.27 જે ઇક્વેશન છે એને કઈ રીતે કરી શકીએ આપણે, ઇન્ટિગ્રેટ કરી શકીએ છીએ by the following equation. So it given us by ln p2s upon p1s. What exactly we do here, only the integration. Okay, is equal to delta h upon r is constant, this term is constant, and 1 upon t square इसका क्या होगा, माइनस 1 upon t होगा. ઓકે, હવે શું કરવાનું છે, 1 upon t square નું ઇન્ટિગ્રેશન, તો માઇનસ 1 upon t square નું ઇન્ટિગ્રેશન શું થશે, minus 1 upon t, upper limit, put the upper limit and the lower limit. If we removing the negative sign, so it will be changed and equal to the exact amount is that 1 upon t1 minus 1 upon t2, and whole equation is that here. Okay, ln p2 raised to s upon p1 raised to s equal to delta h upon r 1 upon t1 minus t2 1 upon t and the value of p1 raised to s and p2 raised to s is the pressure, saturation pressure at temperature t2 and t1 respectively, saturation pressure. Okay, or the saturation pressure is that, the definition of saturated pressure is that at a given temperature or a given temperature the liquid and its vapor, अथवा तो solid and its vapor are coexist in equilibrium. બરાબર, તો આપેલા તાપમાને લિક્વિડ અને એની વેપર બંને શું હોય છે, કોએક્ઝિસ્ટ થાય છે ઇક્વિલિબ્રિયમ કન્ડિશનમાં, બરાબર, તો એને કહેવામાં આવે છે સેચ્યુરેશન પ્રેશર. તો T1 અને T2 ટેમ્પરેચર પર સેચ્યુરેશન પ્રેશર P1 અને P2 છે, બરાબર. So these are the saturation temperature and pressure relations. Now let us see an example to clear more about this Celsius and Clapeyron equations. So from the 6.2 example, calculate the vapor pressure of water at 363 Kelvin if the vapor pressure at 373 Kelvin is 1.101.3 kilopascal. That means heat of vaporization in temperature range is 2275 kilojoule per kg. Okay, so we have to calculate the vapor pressure. So given equation we have to consider this equation. ये इक्वेशन आपको याद करना है, ठीक है. तो इसके ऊपर से गिवन डेटा क्या है, T1 एंड T2 आपको पता है कहाँ पे है. दिस वन इज T1. ओके, कौन सा? दिस वन 363 T1 and this one is T2. Pressure is given that, okay, 101.3 and जो डेल्टा एच की वैल्यू हमें कैसे मिलेगी? टेम्परेचर हीट ऑफ वेपराइजेशन के साथ. तो ये क्या है? T1, T2 एंड P2S. ठीक है, ये क्या होगा? P1 नहीं होगा, ये क्या है? P2S. और डेल्टा एच की वैल्यू 18 के साथ हमें क्या करना है? मल्टीप्लाइड करना है. ठीक है. वाटर का मोलिकुलर वेट H2O. ओके, सो 2275 इंटू 18 एंड गैस कांस्टेंट कौन सा लेना है? 8.314. नाउ जस्ट put into the equation, above equation, so we get the answer, that is uh, P1 raised to S is 70.41 kilopascals.